Okay, so the concept of electrical potential energy is not only for charged particle in a uniform electric field. Let's discuss a case where a point charge is placed in an electric field caused by a static charge distribution. In previous chapters, we studied various charge distribution as a collection of point charges. Therefore, it is useful to calculate the work done on a test charge Q naught moving in the field of a single stationary point charge. This is single stationary point charge. Let's consider a test charge Q naught is having a displacement along the radial line from point A to point B. The force on the charge is given by Coulomb's law, and its radial component would be force or okay. The distance between the test charge and the point charge is R. So it is RA, and this distance from the charge to the B point is RB. Now remember, if Q and Q naught Q naught have same signs, then forces between them is repulsive and your Fr is positive. If Q naught and Q have opposite signs, then your Fr is negative. The force is not constant during the displacement, and we integrate to calculate the work done on Q naught by charge Q as charge Q naught moves from A to B. So work A to B is equal to so work done by the electric force for a particular path depends only on the endpoints. In fact, the work is the same for all possible paths from A to B. To prove this claim, let's assume a more general displacement in which A and B do not lie on the same radial line. So let's draw it. For a more refined figure, you can consult your PowerPoint. Okay, so here is your point A, and let's take point B here, and the test charge is will follow this path from A to B. And this is RA. This would be the distance between this charge and the point B is RB, and the distance between your test charge Q naught and your charge Q would be R. Okay, from our previous knowledge, we know that the work done on Q naught when it displaces under the force of charge Q would be work A to B. Now look into the figure. This is the direction of the electric field and the force is experiencing in this direction on the charge Q naught. And the charge is moving from point A towards point B. It covers small displacement dl. This F cos phi dl is the work done during a small displacement dl along path A to B. dl depends on the charge, on the change dr, this dr, in the distance r between the charges q and q naught, and it is the radial component of the displacement. We resolve this displacement. It showed that this equation is, it showed that this equation is valid for more general displacement as well. The work done on q naught, here the work done on q naught by the electric field E produced by Q depends on RA and RB, not on the details of the path, this one. Also, if Q naught returns to its starting point A by a different path, let's suppose then the work done in the round trip displacement would be 0. These are the needed characteristics of the conservative force. So the force on Q naught is a conservative force. Let's recall the previous equation where work A to B, UA minus UB and here this one is equal to Q naught over pi naught 1 over RA minus 1 over RB. So these two are consistent if we define K Q naught over 4 pi epsilon naught RA to be the potential energy UA when Q naught is at point A at a distance RA from Q. Q naught over 4 pi epsilon naught RA UA. And we define Q naught over 4 pi epsilon naught RB to be the potential energy UB when Q naught is at point B, a distance RB from the Q. So when the test charge Q naught is at any distance R for the charge Q, the potential energy is given by this is electrical potential energy of 2 point charges Q and Q naught. Until now, we have not assumed anything about the signs of Q and Q naught. This equation is valid for any combination of charges. Potential energy is positive if Q and Q naught have same signs. Potential energy is negative if Q naught have opposite signs. So, potential energy is always defined relative to some reference point where U is equal to 0. When Q and Q naught, it happens when Q and Q naught are infinitely far apart. So R reaches to infinity. Therefore, potential energy represents the work that would be done on the test charge by the field of Q if Q naught moved from an initial distance R to infinity. Also, potential energy is a shared property of two charges Q and Q naught. It is a consequence of the interaction between these two bodies. So, we have studied in this lecture electric potential energy of two-point charges. In the next video, we will study electrical potential energy with several point charges. Thank you.